We're now going to look at subtraction fluency. Now, what do I mean by fluency? We're going to get into that later. But first of all, I want you to imagine, again, we're thinking about young learners who are immature in their mathematical ability. They don't know all the details. How do we get them from their natural inquisitiveness and creativity to a more efficient algorithm that we want them to have to be efficient mathematicians? Well, how do we get there? It just doesn't happen overnight, and I don't believe it happens by just jamming it down their throats and telling them to do it. I think they need to have experiences and they need to engage in thinking. So here's a way that we might think through that. So we're going to build procedural fluency of subtraction from conceptual understanding. First of all, we have to go back to what does it mean to subtract? And in the Google slide that hopefully you're in when you watch this video, there's a link to a resource called Achieve the Core that has some details. You can go find this table. This is a common addition and subtraction problem type situation, but I want us to focus on subtraction this time. So for subtraction, it can manifest in a couple of primary ways. Take from or take away. That's the primary way that students first learn about subtraction, is taking away. You know, there's 10 M&Ms on the table and you're going to take 6 away, 10 minus 6. That's a takeaway situation. And you can dig into this link and look at the details. I know you probably can't see this very well, but you can go look at the link later. But the other one is compare. Primary one I want to focus on is compare. For example, I have 10 M&Ms, you have 6 M&Ms. How many more M&Ms do I have than you? See, we're not taking anybody's M&Ms. We just have some. I have some, you have some, and we're just comparing those two quantities to see who has more. And when we compare in that way, we often say it this way: what's the difference? See, I have 10, you have 6. Well, in common, we both have 6 M&Ms. What's different is I have 4 more. That's the difference between my M&Ms and your M&Ms. And so comparing is one way we think about subtraction. So take a look at these two things. And as you do, I'm going to ask you to pause the video a couple times here and actually think. So look at the first one first. I have $76. You have $90. How much more money do you have than I? And what I'd like you to do is actually figure it out. I hope you see it as a comparison. We're not taking money away from anybody. We're just comparing the two quantities. But actually figure this out in your head and see the strategy that you use. Pause the video. Did you do it? Did you compare 90 to 76? And there's lots of ways that this can happen. Kind of back when we were doing doubling 38. There's lots of ways. But here's one. Somebody might go, let's see, 90 and 76. Well, to see the difference, I might start with the 76 and see how many dollars I'd have to count on to get up to 90. We call it the counting on strategy. So somebody goes, let's see, 76, 86. There's 10 more. 86, 87, 88, 89, 90. So I counted up 14. So there's a difference of 14. Other people might literally subtract. They go, let's see, 90 minus 70 would be 20. But it's not 70, it's 76, so it's 6 more. So 6 more, I'd only have to subtract 14 in order to get to 90. See, there's different ways people might think through this in their subtraction algorithm. Now, look at the second one. You saved $3,200 to buy new furniture. You buy furniture for a total cost of $29.98. How much money do you have remaining? Now, this is a takeaway situation because we now, from our $3,200, we're taking away $2,998 of it, and we're going to figure out how much is left. So it's a takeaway situation. But again, I want you to think through this one in your head, and what strategy would you use? Pause the video. Now, I'm going to guess that the majority of you counted on. You went $29.98. 2 more get you to 3,000, and then 200 more get you to 3,200, so 202. And I share this one, and I made it up this specifically the way I did because When I've done this in live audiences, I'm going to again make up a statistic here and say about 99.9% of people do not do this. All right, I started with $3,200. I subtracted $29.98. And so now I'm going to go through my old standard algorithm that I learned in elementary school. Let's see, I can't subtract 8 from 0, starting over here on the right. I can't subtract 8 from 0, so I'm going to look over here. I can't subtract 9 from 0 either, so I'm going to go over here. I'm going to borrow, so I'm going to cross off this 2 and make it a 1 and bring it over to here. Then I'm going to subtract that by crossing that off and making it 1. And you're going to go to and get 2, and then you're going to subtract and get, and then I have to subtract or borrow from here and get it here, and then 11 minus that. Nobody does the standard algorithm because it's so inefficient in this case. Wouldn't it be more efficient to go 29.98 and then count up? Count on. 29.99, 3,000. 3,200. So 202 would be the efficient way. So I share this because, first of all, strategies. Are we comparing or are we taking away? Second of all, how are you going to engage in that subtraction? Okay, certainly you can use a calculator. Certainly you can ask Siri. You can do all those things too. But if you're going to think this one through, you might think in different ways, and counting on might be a good strategy. All right, so back to algorithms though. We do want to develop even a traditional algorithm. I'm not saying that we don't ever want to teach this traditional algorithm. What I'm saying is, how do we get students to make sense of it, to leverage their natural inquisitiveness and curiosity and creativity? How do we get them there? And part of fluency, do we always want them and only want them to do this? I say no. In this case, I don't think that's the most efficient way. So how do we help students to choose an efficient strategy? Is counting on more efficient? Is doing the algorithm more efficient? Or is there some other strategy that's more efficient? That's where we're going next. And so again, learning theory, purpose and meaning, leading up to facts and skills. So I think students are motivated to learn when they're doing things in context. And so here's a context from my real life. When my Andrew is my oldest son, Zachary is my youngest son, but back when they were young, that's why I said was. Back when they were young, they collected baseball and football cards. And so Andrew had 332 baseball cards, and he gave some of them to his baby brother Zachary. Can you believe it? He gave him 157 of them. How many baseball cards does he have left? So I might pose that to kids learning about multi-digit subtraction. And for a minute, ignore all my instructions here because we have to work through this. Hey, if you've got that base 10 block app, get that base 10 block app out and will you play for a minute? How would you use the base 10 blocks to do this subtraction problem? It's a takeaway. Andrew's giving away, or Zachary's taking away 157 of the baseball cards. How many are left? That's a takeaway problem. But will you first try it on your own with base 10 blocks and kind of imagine a young learner engaging in this for the first time? How might it look? How might it sound? Pause the video, open up that app with base 10 blocks and give it a go. All right, here's my style of doing it based on observation for so many years. Here's my first observation. Maybe you did it too, maybe not. But first of all, students say, all right, I need 332. I need to represent 332. And then we're subtracting 157, so I have to represent 157. It's pretty common for students to put out blocks representing both numbers. Why? Well, because we just got done at adding. And when you add two quantities, you're going to combine those two quantities together. And so it's pretty common to start with the two quantities and then push them together. But in this case, we're not doing that. We're starting with 332 and we're taking away. And so even with my adult MAT256 students, sometimes we have to have a little conversation and go, did you really need to represent 157 in a takeaway situation? And they say, no, we really didn't. Because what we're going to do is we're going to start with 332 and then we're going to take away 157. So there's where we start with 332. All right, then here's usually how I see it. Again, I can make up a statistics if you want, but a large percentage of students from actual young learners to my MAT256 students often start with this. All right, 332. We're going to take away 157. Guess where they start? They take away the big ones first. They first take away 100. So now 332, take away 100, we're down to 232. All right, next, I'm going to take away the 50. I took away 100. Now I have to take away 50 of the 157. And here's where they run into some trouble. It's hard to take away 50 when you only have 30. So we have to do some problem solving. And this is where the place value thing becomes so important. Kids who have been engaging in place value thinking, like you have been engaged in place value thinking, have a strategy now, have an understanding that they can not only put tens together and move them to a new place and a new value, they also understand that you can take tens apart. Putting tens together and taking tens apart is a common thing we do with place value for this purpose. We're getting ready for a later grade so that when students get here, they go, I need to take away 50. I only have 30. Oh, but what I can do is take one of these hundreds and break it apart into 10 tens. You see it now? Maybe you didn't see that coming back when we're doing place value, but this is so critical that this is a thing that we've set up. In our state standards in Arizona, and for most of the country, by the way, the standards are written to have a progression or a trajectory through them. So there's things that are happening in kindergarten, in first grade, maybe with place value, like this, so that when students get into second or third grade and they're doing multi-digit subtraction, we're setting them up for that future. And if we take away that learning goal, if we take away that putting together and taking apart with place value, we've left a gap, we've left a hole for when we get to this. But now look, students now have 100, and now this second 100 is now 10 tens, and then 3 tens, so they still have 232, but now they can take away the 50. And so we take away 5. I took away the 5 right there. Did you see it? Did you see it? Did you see it? I took away the 5. And so now I have 182. And finally, so I took away the 100. I took away the 50. Now I have to take away 7. I have to take away 7 single cubes. And I don't have 7, I only have 2. So once again, students would have this strategy of grabbing one of their tens and breaking it apart into 10 ones. Let me do that again. Make sure you saw it. I took a 10 and I broke it up into 10 ones. So it's still the same quantity, but now I can take away 7. And so I'm going to take away, it doesn't matter which 7, I could take 2 from here and 5 from here, I could take all 7 from here, do it however you want, it doesn't matter. I think I took 7 from down here, yep, I did. So I took away those 7, and then what's left? And what's left is 175. All right, so with the manipulative, with the hands-on manipulatives, students are able to reason through this. I hope you can see it, especially if they've had experiences with base 10 blocks and place value. Now it's just a natural thing to do, but this is where it gets fun. Suppose students use the manipulatives as I've shown, and I don't mean to say that every student's going to do it exactly the way I did it, but they're going to do whatever they're going to do. But now I would say, all right, students, capture what actually happened using numerical symbols. So let's say they did. All right, well, we started with the 2 quantities, and I realized I didn't need that 157 quantity because I'm going to take away 157 from the 332, so I just needed 332. That was my first step. And I first removed 100. So student recorded it. I started with 332, and I took away 100, leaving me with 232, and they record what happened. All right, then the next thing I did is, since I had to take away 50, and I only had the 3 tens, I had to take one of the 100s and break it up into 10 tens. So now look, I have 10, 11, 12, 13. I now have 13 tens. So I have my 100, plus I have my 13 tens, which is 130, plus those 2 right there. So that's what I did next. And then next, I actually took away the 50. So from the 130, the 13 tens, I took away 50, and so now I have 182. All right, after I have my 182, I had to take away 7 more, but I didn't have 7 to take away. So my next move was to take one of my 10s and break it up into 10 ones. So I now had the 100. I have 1, 2, 3, 4, 5, 6, 70, but then I have 10, 11, 12. I have 170, 12. Yeah, I have 170, 12. And from that, I can take away 7. And so I took away 7 from the 12, leaving me with the 5. So now I have 175, and that's what I did. And so the record keeping might look like this. Very inefficient, maybe unorganized. And so this is where we leverage students' creativity, their thinking, their inquisitiveness, and you give them a challenge. And you say, hey, student, can you organize your thinking a little bit more neatly, a little bit more efficiently? And we practice this with different problems, different times over maybe days, and they practice their algorithms. And so suppose now we have done that for a while, and students have, I'm going to show you a few different ones that I've seen. And what I'd like you to do is take a look at what the students did to answer the question and discuss the advantages to using their alternative algorithm. Now remember, these are students progressing from hands-on manipulatives to writing out what they did, working on their efficiency, getting more organized. And so this is sort of the end product of all of that work. All right, now pause the video and examine just the one on the left. The one on the left is the situation with 332 minus 157. Pause the video and see if you can make sense of what happened here. All right, I hope you took some time to think through this one, but this one's interesting. And when I've done this in the classroom with students and teachers, there's sometimes been a little bit of debate, a little bit of disbelief. Let me show it to you. Student looks at this and says, well, I'm going to start over here and say 2 take away 7 is negative 5. And then 30 take away 50. Notice this is not a 3 and a 5. This is 30 and a 50 because place and value makes a difference. 30 take away 50 is negative 20. And then 300 take away 100 is 200. And then they looked at this and said, if you put all this together, 200 and the negative 20 collect to make 180, and then 180 take away 5 more is 175. Whoa. That works, doesn't it? 175. But here's where the debate comes in. Negative numbers, really? Well, it depends on your context. Maybe in the Valley of the Sun here in Phoenix, Arizona, maybe no kid would do this. But where I grew up in northern Minnesota, negative numbers were natural because we lived it every winter. Thinking about negative quantities was not a big deal for very young learners. And I would even argue, I challenge you, if you have access to young kids, ask them things like, what would 5 take away 9 be? Maybe even before they've been encountered negative numbers, and see if they have a way of making sense of that. But I can tell you, kids that live in cold climates, to say it was like 2 degrees outside and the temperature dropped 7 degrees and now it's 5 below zero, something like that is not a stretch of the imagination. And so depending on the context, you might have kids that can do this. Now, does this work even if this strategy, this methodology, does it work even if you don't have negative numbers? Yes. Now come over here. Pause the video and see if you can track the thinking in this case. Pause the video. All right, so this student that has this strategy can employ this strategy even in this case. I had 368, and maybe by the time they get to this stage, they've got a mental image of those blue blocks, those base 10 blocks. They can imagine 300s, 610s, 8 ones, and I'm going to subtract 100, 2 10s, and 5 ones. And if you subtract 5 ones from the 8 ones, you'll have 3 ones left over. And if you subtract 2 10s, 20, from the 6 10s, you'll have 4 10s or 40 left over. And if you subtract that 100 from that 300, you're going to have 200 left over. And so altogether, what do you have left over? 243. Now, what's the advantage of this? The advantage of this is, let me back up a minute. Where did I do it? Where did I do it? Hang on. There, I did it. The advantage of this is the thinking is so clear. You don't have to borrow. You don't have to wonder what it is when you put little numbers up there. You can just think. And some students who have really owned that strategy because they went through that progression of very concrete manipulatives to less concrete drawings to more abstract symbolic representations, kids who have been through that progression can subtract with that style very efficiently, I will argue. Let me go back there. And they'll write this down. So they don't have to borrow. And you know what? Borrowing is weird anyway. Because for a kid, when you borrow from the tens place, you never put it back. So it's not really borrowing. In fact, a better word to be used there, and I'll show it to you when we did it, say, right in here. When we took a 10 and made it into 10 ones, it's borrowing from our traditional language. But a better word to use there would be exchange. We exchanged the 10 for 10 ones. So I would encourage you to encourage that language with your kids that you're exchanging, not borrowing. But anyway, back to this. There is no borrowing. You're just subtracting. And when you're done subtracting, and you can imagine those blocks, took away 5 little ones, took away 2 tens, took away the 100, and then what do I have left? 243. It goes pretty smoothly. Now, another student did this. Will you please pause the video and make sense of what happened here? I'll give you a minute. Go. All right, I hope you did it. This student did the counting on strategy. I hope if you go back to the what does subtraction mean? Counting on is a good strategy in some cases for some mental math. So this student said, to subtract, I'm going to count on to the 157 until I get to 332, and I'm going to see how much I had to count on. That's the same thing. And this could be done very efficiently and could even be done mentally, depending on how you do it. Now, as I show this, please understand this is just what a student did. So it may not have been the most efficient way to count on. It was just the way the student did it. And here's what they did. To count on, they first knew to get 157 and count up to 332, they knew they could start with a big 100. So I'm going to count on by adding a 100. That gets me to 257. And then maybe the student could, easily in their brain do 50 more. And if you did 50 more, that would get you to 307. Ooh, we're getting close to 332. And then they added on 20 more. That got them to 327. And then 328, 29, 30, 31, 32. 5 more will get me there. So this student just happened to start by counting on with 100, and then they did 50 more, then they did 20 more, then they did 5 more. And all together, 150, 60, 75, 175 got counted on. And so the subtraction, the difference is 175. Beautiful, beautiful. Counting on is a good strategy. And sometimes I get pushback on this, like, well, shouldn't the students just do the old algorithm? It's so efficient. I say efficiency is in the eye of the beholder. A student who can do this will do this much more efficiently than if you force them into that awkward borrowing standard algorithm. They might be more efficient at this. So just consider that. Try it. Talk to some kids. See what you can learn about that. All right. Hey, I'm going to pause it here. After we come back, I'm going to tell you the story of second grade Gretchen doing some subtraction.